Welcome everyone. Today we have Dr. Francisco Villaescusa-Navarro, the research scientist at Center of Computational Astrophysics at the Flatiron Institute. And well, fun fact, he supervised me for my master's thesis, so I'm like really happy that he's here at my new institute. And well, I will let you take the floor.
Thank you, Arnab, and yeah, thank you for the invitation. Of course, it's a pleasure for me. I think it's the first time I was taking Yandu. I'm here, but I need to come back. So oh, there is. Let me remove this. So the idea of this talk is mostly to tell you a little bit, the things that we have been doing recently with many different people about, how to combine numerical simulations with machine learning to basically learn about the fundamental physics. So let me see if now I can move. There you are. So yeah, so the idea is to tell you a little bit about the motivation. I was maybe not assuming that everybody will be a cosmologist. So yeah, maybe some of you will find this part boring. So what kind of is like the big picture, the things that we are really trying to do. And then talking about things, the role of numerical simulation, which is basically what I think the community has been doing maybe in the last 5 years, and now how machine learning and AI is kind of really, in my opinion, revolutionizing the way that you do things. And people in Zoom, I am assuming that you can hear me well, but please, yeah, let me know if. All right, so this is what the ChatGPT think cosmology is. We usually don't dress so nicely, but I really like this kind of image because I think it illustrates a little bit what cosmology is. So if you were able to put the entire universe in a crystal ball, cosmology basically is the branch of astrophysics that will study basically everything inside the crystal ball. So the things that we care is like, what is the origin of the universe? What is the fate? What is the composition? What are the laws of the universe? So this kind of really fundamental pieces. So for the cosmologists in the room, I mean, all of you know this very well. We believe that this is the composition of the universe today. Only 5% of its energy content is basically things that we know, every material, every atom, every single thing that we know is only 5% of the composition of the universe. Around 25% is like dark matter. So, we believe some kind of fundamental particle, but I still don't know what are the properties about this. And then dark energy, right? We have very little idea about what this is. But this is basically, we call this whatever is responsible of the accelerating, the recent accelerator of the universe that we have a lot of evidence for it. So, things that we want to address is, what is the nature of dark matter? Is all dark matter, is all dark matter, is atomic dark matter, what are really the properties, microscopical properties of dark matter? For dark energy, we want to know what is the nature of it, it's a cosmological constant, is some other property about, maybe a different force in the universe, and these kind of things. So, in cosmology, we have an amazing model that is called the lambda dark matter model. And sometimes when I talk to more, let's say, computer scientists, I always make the joke that we have done the biggest dimensionality reduction ever. We have a model that basically, with a set of parameters, we are able to explain pretty much anything in the universe, right? So imagine being able to explain the entire universe with 5 to 10 parameters. This is really remarkable, right? And this is something that, as a community, we have done. So, we have a model, the model works very well, and we have some parameters. So one of the most important things in cosmology is to measure these parameters, with the highest accuracy. That's really kind of the name of the game, one of the most important things. And, if you're not familiar with these things, so why do you want to do this? So the idea is that we don't know, for instance, what is dark energy. We don't know what is dark matter. We don't know what is the composition of the universe. So what we want to do is to constrain these parameters with the highest accuracy, because we want to discriminate between different hypotheses. For dark energy, we saw that there is maybe property of the vacuum, but maybe there is something else. In order to discriminate these two things, being able to put, let's say, the smallest error bar will allow us to discriminate between these two things with the highest degree of confidence. So that's really our main goal. For those of you not familiar with cosmology, we want to, we have a model. The model has some free parameters, and we want to constrain these parameters with the highest accuracy. And of course, please interrupt me at any time. I have given this talk so many times, so please. So, how we have been doing this historically. So you need two things. You need observations, and you need a theory model. So the idea is that you measure something on the sky, and in this talk you can think that we measure the position of galaxies on the sky. Some angular position and maybe some kind of distance. Until recently, we didn't know how to work with this kind of raw data. If someone gives you like a galaxy catalog, there is a galaxy here, another there, another there, another there. How do you work with that data? So we have never really worked with the raw data itself. So historically, what we do is to compress the data into a low-dimensional vector, right? So, you have, for instance, in this image, and you can really do any data compression that you can imagine. You can, for instance, count the number of galaxies. This is a way to compress the data. You will lose information by doing this, right? Because this image, will have 1,000 galaxies. You can put all the galaxies, like this, and it's still going to be 1,000 galaxies. But the images are going to be very different. So, historically in cosmology, we use something that is called the power spectrum. Many of you are familiar with these things. And we do this for very good reasons, because we know that on some particular cases, this is kind of the optimal way to compress the information. So, if someone gives you, let's say, a Gaussian density field, the universe on larger scales, or on sufficiently large scales, this is optimal. It can be shown that this is the best way. So, but it doesn't matter, you can compress the data in any summary statistics that you want. And then from the theory side, what you do is given the values of some cosmological parameters, you can make a theory prediction for how this data vector will look like. And then the idea is to compare your observation with your theory, right? And historically, we write down your likelihood, and you basically maximize your likelihood. And from a historical point of view, what we have done, maybe thinking about 1 or 2 decades ago, is pen and paper calculation. And the reason for this is basically because we are physicists, and this is kind of historically the way that we do things. And if we didn't have supercomputers, very much this is what we have. So the idea here is that you can write down the equations governing the universe, and we know these things. On sufficiently large scales, we know very well the laws governing the universe. And you might not be able to solve the equation directly, right? They are too complicated. But the typical tricks that we use is you take your equation, maybe you linearize your equation, then it can be solved. And still the solution will be valid on some regime. And then, you can do maybe post-linear correction, right? It's like linearized equation plus some perturbation. And then, there is an entire field of perturbation theory, people trying to push to a little bit smaller things. These approaches are great. It can be shown that this is very rigorous, and still this is pretty much this is still kind of like the standard approach that even today we use to analyze the data. But the most important limitation here is that because we are solving the equations in the linear or in the perturbative regime, we are losing information, right? Basically there are regimes where the equations are not valid in the linear or in the perturbative regime, basically in the nonlinear regime. So then, you are limited only to some particular cases. Or in other words, you are going to lose information by using these things. And that's why, this talk is a little bit about how we can tackle this problem. So the first solution is to use numerical simulations, right? I mean, why should play? Yes. So, why do you need to solve the equation analytically if you can just solve them numerically? So this is an example of how you can solve these equations numerically, this is an n-body simulation. So we have basically dark matter, and the only force that we put here is gravity. And on sufficiently large scales, gravity is the relevant force, right? Other forces, electromagnetism, nuclear force, all these kind of things are completely irrelevant. So on sufficiently large scales, gravity really is what shapes the universe. And that's why we run this kind of numerical simulations where you have, let's say, dark matter, even though dark matter here represents dark matter and baryons. And you can see how, let's say, structure formation proceeds. So you start the universe being very homogeneous and isotropic, but there are very small fluctuations that are, let's say, above or below the average. And what gravity does is basically amplify these things. You might have some region here where there is more dark matter, and basically gravity will start clustering and accumulating dark matter. And then you will form this structure that are called dark matter halos. Dark matter halos are connected by filaments, regions where the density of dark matter is a little bit lower. And then there are regions where there is a very, very low density of dark matter that is called bonds. And again, I think most of you are familiar with this, but I was assuming that not everybody. So that's why, yeah. I told you that I spend way too much time with the movies. So what I want to illustrate with this movie is why we can do cosmology. So what you can see here are two universes. There is one here, and there is another one here. The two of them have the same initial conditions. The only difference is that I believe in this one, there is a little bit more dark matter than in this one. So take a look at this halo, for instance, and it goes from one universe to the other one. What you can see is that the position of these dark matter halos change, but also the internal properties of the halo. Like, for instance, the mass, the mass will be different, but also things like the concentration, the way that dark matter is distributed inside the halo will change. And these guys are not kind of random things. These are basically the environments where galaxies live. So you should basically think in these things on objects where you will have several galaxies inside. So I think the way that you should see this is that, you have a distribution of galaxies in this universe. You have another one, now there is another thing here, but forget about this. So what this is showing us is that if we change the composition of the universe, the distribution of galaxies in the universe is going to change. I have another movie to show you what happens if you change the laws of the universe. So in this case, we have the traditional law. So dark energy is just a cosmological constant. In this case, we have one of these theories that tells you that maybe dark energy is something else, is a modification of standard general relativity. And the same thing, when you change from one universe to the other one, thing changes. Let me see. Yeah, way too many movies. So this is for another thing that we did recently where you even inject some particular thing to the initial conditions of the universe. In this particular case, what we did was to inject like a parity violation term. So, in general, we believe that the universe should respect parity. So, if you do a parity transformation, if you put the universe into a mirror, it should be basically the same thing. In this case, it's not. And what you can see is that this is a universe, and this is kind of like the mirror of it. And this is kind of showing like the differences between them. So you can clearly see that there are differences everywhere. And maybe a little bit more easy if it's a little bit hard. But even when you change the initial conditions in the universe, the distribution of galaxies will change.
The right of the residuals.
Exactly. Or the rise of the residuals. So I think, for instance, this one is this thing minus this thing. And this is like this minus this. So you can see that there are small residuals, but they are. If this will be perfectly parity violation, this will be black. Everything will be black. So in this particular case, what we do is that at the level of the initial condition, so gravity by itself should not violate. It doesn't really matter. I mean, the force like this or like that is exactly the same. But in this case, it's like when you start already with your, let's say, initial conditions with the distribution of matter, that distribution of matter is not symmetric. If you take, let's say, your field and you do a parity transformation, then that thing is not the same. If it's on those. Exactly. In this case, it's because we inject a term that is not constant. That's exactly the point. There has been recently some work, some people playing with that. There might be some parity manipulation in the universe. That is something very, if this true, is very important. So we try simulation techniques.
So may I ask?
Please.
So these the purple points in the movie on the left are big halos, right?
Exactly.
Not galaxy-sized halos, not clusters.
That's a good question. I don't remember exactly. This is probably a 10 to the 14 solar mass. This might be a cluster. And these small ones, yeah, these are like maybe 10 to the whatever. This is like an M-body, but not super. So putting all this in together, with all these movies, I just want to say that whenever you change the composition of the universe, whenever you change the laws of the universe, whenever you change the initial condition of the universe, the distribution of galaxies are going to change. And in cosmology, we actually use the opposite. So what we do is, so we observe directly the distribution of galaxies. And what we want to do is to infer the cosmological parameters. Given the distribution of galaxies, we want to infer the composition, the laws, and the mission. Please.
So in the residuals, are the residuals more common when the masses are higher?
That's a good question. So let's look at
it. Looks like
I see bonds and filaments.
yes, and following the structure.
Yes.
So it looks like there's some correlation the residuals with the structure.
Yes. For instance, this is a big guy, but I don't see a lot of residual there, right?
I think there's the bonds in there.
Yeah.
Yeah.
Okay, that's to be expected, right? The gravity conserves fire.
Exactly, yeah.
So basically, propagates in this condition.
Yeah.
Okay.
But I don't have a lot of intuition to read this. But yeah, that's all.
Yeah, for example, you can see the residual is matching but the mass is not. Yeah,
Yeah.
Because it wasn't matching. In any case, sorry.
No, thank you. So, what I think the community has been doing recently has been, if you are not able to solve the equations analytically, as we were saying before, let's just run simulations. And, this is one particular set of simulations that we have run for many years. Yeah, this is like the largest set of embodied simulations ever run. We have more than 85,000 full embodied simulations. You cannot imagine how many complaints I get from the system administrators. They hate it. It's like, don't come back again. So, very good question. So, most of them, they assume that it's flat. But we have simulation where we vary this thing. This is like the DC mode. So, basically, in this case, we have a curvature. But very few of them. Most of them, yeah, we assume. And, I mean, there has been a lot of work also with other simulations. And I don't really want to basically spend time on that. I think, the community, I think both, right? The large scale structure, so galaxy clustering and width lensing has probably reached agreement. And it's that, if we use the traditional way that we use in cosmology, so you take your data, you compress, maybe using this power spectrum, then you're going to lose a lot of it. And what people have been shown, maybe in the last 5-10 years, was that, if you are able to use other ways to compress the data beyond the power spectrum, people have tried power, spectrum, not power spectrum, voids, and Luke has done a lot of work on the issue of wavelengths, voids, all kinds of things. And as you go to a smaller and smaller scales, there is a huge amount of information that we can store. And these are things that we cannot do with, let's say, linear theory, because it's very hard to make theoretical predictions for all these things. But if you have enough simulations, you can just basically compute these things.
But this is going to smaller scales. Other forces we can import around that gravity. Right? So then the regime is really
Exactly. And that's exactly what I'm going to talk right now. That's a super good thing. So exactly as you were saying, the problem is that as you go to smaller and smaller scales, we need to start worrying about other pieces that in our simulations we can. So let me explain. So this is a galaxy, a cartoon of a galaxy. In the center of the galaxy, there is a supermassive black hole. And you can see that the supermassive black hole is releasing this gigantic amount of energy. So the thing is that this energy is going to change the properties of this galaxy, but it's also going to change the properties of all the other galaxies nearby. And let me show you with a movie exactly this. So this is now a hydrodynamical simulation where we take into account gravity, but also hydrodynamics. So this is a galaxy, and in the center of this galaxy, there is a supermassive black hole, and you can see that it's releasing all these very high, very hot gas. And this hot gas can propagate like very, very far away, right? So it's going to affect also galaxies that are very far away. So exactly as you were saying, the problem here is that we cannot even write down the equations that govern this, let's say, supermassive black hole theta. But we don't know exactly that physics. So that's really the big problem here. It's like, we have a lot of evidence that these astrophysical processes exist. We have seen this all the time. But we don't know the physics of it. So, we know on one hand that as we go to smaller and smaller scales, there is a lot of information. On the other hand, we need to deal with these kind of things. We need to deal with things that we don't even know exist. We don't even know how to write down the equation. And this is where I think the role of AI is planning to play, and something that I think is going to be very important. So it's going to allow us to basically tackle this problem. So ideally, what you want to do is like, if you don't know the physics of this thing, even if you know that these processes are there, what you want to do is to marginalize even, right? There are, maybe somehow you are able to parameterize the physics in some way. And what you want to do is to marginalize over these free parameters or whatever you want. Or if you have a model to simulate these things, you want to marginalize over the model itself because the model is probably. So before explaining a little bit more into detail, let me talk now a little bit what is a different way to tackle this problem. We said before that if there is, if we have like a galaxy catalog, people traditionally have been compressing this into a low dimensional. So, with deep learning, I think we can do something different. So imagine that you have every star here represent like a galaxy, right? And this is really what we observe. We observe one galaxy here, another here, over there, something like that. And the question is like, can we just work with this data by itself? Because this is really what we have. We have a galaxy catalog, we have positions of galaxies. So the traditional way of doing this is maybe putting this into a regular grid. And then you can use things like CNN, this kind of things. The problem of using this approach is that, if you have a regular grid and you have a voxel or a pixel, you cannot extract information on scales below the pixel, right? Because you don't know if you have two galaxies or what is the internal distribution. You can say, okay, I'm going to take a grid that is so fine that I will only have a maximum one galaxy per voxel or per pixel. That's fine, but you will end up with a gigantic grid where it's going to be mostly filled with zeros and it's not going to be open. So another way is basically to represent the data as a graph, as a mathematical graph. And, this is one particular representation of this data. And mathematical graphs are characterized by basically three properties. So one of them is the nodes. So the nodes in this case are where the galaxies are. And the nodes can have features. And you should think about this like some vector, right? So this could have like the position of the galaxy, but can also have like maybe the stellar mass of the galaxy or velocity, whatever property you measure from the galaxy. Then we have the edges. So the edges are basically the connections between the nodes. And this is also like a vector. It can have some features. So, in this case, could be like the distance maybe between the nodes, but it can be other things like angle, these kind of things. And then you can have like global features. This entire graph might have 20 galaxies, so this is a global feature. Or this graph might live in an overdensity, so that overdensity is a global feature, these kind of things. So, this is an entire field in mathematics, as far as I know, and people have been working on this for decades. The thing is that in deep learning, we have a mathematical structure that can deal with this kind of thing. And these are called like graph neural networks. So let me explain how these things work. So imagine that you have a graph initially, right? So you can have like a galaxy catalog, and then somehow you connect the galaxies. And I'm going to explain later how you do this. And then you will have some node features and you have some edge features. So the idea is that you will have one of these graphs and you will pass into a graph neural network layer. And the graph neural network is going to give you basically the same graph. It's going to be exactly the same thing. The only thing is that now you are going to update the properties of these features. And the way that it works is the following. So you start with the edges. So imagine that you start with this guy. So what you do is you take the properties of the edge, you put it there, and then you take the properties of the nodes that are connected, that are basically on the edge. And what you do is you take all the properties of all these things, and you concatenate this, and then you create like a longer vector. And then you pass this to a fully connected layer. And this is the way that you update the edge feature. So you go from this edge feature to this one. Please.
In practice, each galaxy should have the same number of edges, right?
You mean that every galaxy should have the same number of edges?
Yeah. Otherwise, your network would be dependent on the number of edges that you have.
That's a good question. So this is like for this part. So for the edges, you will always have like two nodes connected to it. In this case, if you have an edge, you will always have like two nodes. But now it's like if you have a node, you can have different number of edges. And now how we deal with this? So let me explain. So now imagine the second thing that you do, you update the edges. Now you need to update the nodes. So on the nodes is like, you can take this node and you take the properties of the node, you put here. And now what you do is you consider all the edges. And as Luke said, it could be 1 edge, could be 4 edge, could be 300 edge. How do you deal with this? So that is when you do this. I remember the first time I saw this symbol. It's like, oh my God, I have done something wrong. So what this means is that this is a permutational invariant operation. So things like the sum, the maximum, the minimum, the mean, the median, all these kind of things. So, it doesn't really matter how many edges you have, because you are computing this permutational invariant operation, like for instance, the sum, then it doesn't matter how many edges you have. And then, you can also put like global features and all these things. You can also put global features here. So you put all these things together, and then you pass this to another fully connected. And then you go, let's say, from this node feature to this node feature.
Are you not using some fundamental physics here by averaging style?
Say again?
Are you not using some fundamental physics in this process by averaging?
Yes, you are. It can be shown that the graph neural networks are not universal approximation functions. So by doing this, you lose a little bit of expressivity. So yeah, you definitely lose information. For instance, if you imagine that this is like the sum, you are losing information, right? You are computing the sum, and the sum will give you something, many different combinations of the edge features can give you the same sum. So you are going to lose information by doing that. So people still are working on even how to go to higher order these days. I believe people use these topological neural networks. I'm not super familiar, but yeah. So the idea is that you start with a graph, you do this, you apply this graph layer, so you take the same graph now with all the properties updated, and take into account that why this would be interesting for us. We know that in cosmology, all the scales are kind of correlated. The galaxy here will also care about this galaxy here. But if I only have one graph layer, this node only knows about this and this and this. Doesn't know anything about this. There is no way that you can propagate this. So the trick here is that you can do one layer, or you can do like 2 layers. You can do the same as with CNS, right? You can do n layers. And then when you do n layers, initially this guy was only sensitive to this, but this was also sensitive to that. So now this one already becomes to this. So it's kind of a way to take into account the entire, let's say, distribution of the graph. The other beautiful thing about this is that a graph can have 10 galaxies or can have 2,000 galaxies. It doesn't matter, right? This is really designed to work with sparse and irregular data. So you can do this 10 times, and at the end of the day, what you do is you take all the node features that you have, you do again this permutational invariant operation, and then you end up, you pass this to a fully connected, and you end up now with a fixed size feature vector that you initially define, probably 50 dimensions or 100 dimensions or 5,000 dimensions. But this is kind of the beauty, right? You start with a graph where the number of galaxies or nodes is arbitrary. But with this kind of formalism, you can end up with a feature vector that will always have the same number of features. And now with this, you can do your SBI, whatever thing you want to. So for instance, in this case, what you can do is apply SBI directly on the graph, and you go from the value of the cosmological parameters to basically the galaxy positions to the value of the cosmological parameters at the level of the graph.
So for Euclid, we have several millions of galaxies, so
yeah,
scale.
Yeah. With this like brute force, it will not scale. I think there are ways. So I was recently. That's why sometimes I think astrophysics we are way behind. I remember they invited me for a more computer science conference. So I went there. It's like we are doing this thing in cosmology, super nice, but we cannot deal with 1 million galaxies, right? It will not fit in the GPU memory. All these things.
What the limit?
For this, I'm able to do 15,000 galaxies, something like that. I can probably push a bit more, but I cannot do 1 million. But then people told me, we are doing this in Facebook with 1 billion users, right? So I'm pretty sure there are ways. It's just that probably we are not. Yeah, Victor.
No, it was just a question if it makes sense to have a multi-scaling graph where you can average properties of different galaxies in scales, and so it creates larger scales, but with a lower amount of galaxies inside.
Exactly. So there are different flavors for this. There are these hierarchical GNNs, that is, I believe, what you are talking, where you have all this hierarchy, and yeah, you can do this thing. Recently, because that you're interested, I've been playing with different architectures. You can have a GNN, but you can also have a transformer. A transformer is basically a GNN where everything is connected with everything. That's a transformer. Or you can have a deep set, where it's basically you don't have any connection. And there are mathematical theorems that tell you that a deep set should also be universal. And what I can tell you is that all these methods give you the same answer. But a deep set is way easier to train.
Sorry if you can talk about it next, but it's a neural network, right? So what's the loss function that we might do?
Very good. So in our case, we do some SBI, but basically you can think of this like, we do
SBI.
We do some simulation-based inference, but you can think that, we do regression. So the loss function is a mean square error. You can think about that.
What's the ground truth?
The ground truth. So in our case, the galaxy catalog is coming from a simulation. So the ground truth is the value of the cosmological parameters. that we know. And then you train the model to go from, let's say, galaxy positions to the cosmological parameters without using summary statistics or anything like that. The other beautiful thing about this thing is that there is really no like a minimum scale, right? If you think about this, you can have two galaxies as closely separated as you want. The graph will still extract information from them. This is very different to the CNNs or to the grid, but you have really like a pixel size.
Yeah, but then as soon as you work on real position, and like you do graph versus a grid, there is always a question of computation time. The grid is a way to save a lot of computation time. Is the price to pay is you lose some information at single speeds.
Exactly.
So here you're mentioning 2,000 galaxies, while surveys actually like this is 100 millions of galaxies. So it's interesting that you can do that, but here you don't scale at all. Even with actual survey, I'm not sure about the SST.
Exactly. I mean, it was really, we are kind of exploring these things. Yeah, in practice, yeah, probably these things. And yeah, you need to deal also with your theory prediction on super small scales if you trust these things. But let me show you an example. Okay, and for maybe those of you maybe more familiar with machine learning, it's very easy to implement the symmetries of your problem with these graph neural networks. So in our case, the model is by construction E3 invariant. So it's translational invariant, rotational invariant, and also parity invariant. So what we do is that we don't use positions for the nodes, right? Because if I take the graph and I rotate it, the positions are going to change. So all the spatial information is for us coming in the edge. So what we do is that the edges basically contain the distance between nodes. And if you have distance, you can now rotate the graph. The distance is not going to change. It's always going to be the same. If I translate the graph, the distance is going to be the same, right? And on top of this, what we do is to basically compute these kind of angles. We compute all the scalar products. So you have distance and you have angles. You take your mode, you have your graph, you do an E3, let's say, transformation, nothing is going to change.
But the vectors change when you rotate.
The vector changes, but what we use in the network is basically the scalar products of the vectors. Okay. So angles and distances, and that doesn't change. Okay. So that's the trick. So, very beautiful very simple to impose here all these symmetries. And, people have shown that, by imposing the symmetry instead of learning by data augmentation, things work better. All right. Let me just maybe mention how much time. When should I stop? 5 minutes. Okay.
So if I understand well, so you are using zero graph neural network as a summary statistic.
Yeah, let's say that, it's kind of your data compression in that case.
Would you compare to any other summary statistic like bispectral or things?
We compare with the power spectrum, the traditional one, and we do better.
Statistics.
Exactly. I don't think we did with the bispectrum. So that's a good... the things that here we don't really have like a minimum scale. So you might need to really compute these two. It's very expensive to compute the bispectrum to super small scales. But at the level for the power spectrum, we did better. So now let me talk about the data that we use to train this graph neural network. So this is coming from this CAMOS. So CAMOS is stand for Cosmology and Astrophysics with machine learning simulations and more videos. So what you can see here is one of the simulations that we have in CAMOS. This is also the largest set of simulations ever created. We have more than, I think, 12,000 right now. So imagine the system administrators, how angry they are with me. So in blue, you can see the gas density. In red, you can see the gas temperature. And you can see all these explosions going on. These are either supernova explosions or supermassive black hole releasing energy. So this is really the very best theoretical prediction that we have right now. Yeah, these simulations are really, really expensive, but this is right now the most accurate theoretical prediction that we have if we want to simulate the position of galaxies and all these problems. So this simulation gives you like very pleasant.
What is the scale of this?
So every box here is like 25 megaparsec. So it's not super large. This is now much smaller. And I think we are able to resolve, in this case, halos of 10 to the 8, like that. But this is much higher resolution. And yeah, this simulation gives you like very accurate theoretical predictions for the phase space of dark matter, phase space of gas, also all kind of properties of gas, like gas density, temperature, pressure, all these kind of things.
So you start from C10,
We start from Redshift 100.
100.
100 is just to make the movie not happen really.
So you follow the ionization and everything.
Absolutely. Yeah, these are really, really expensive simulation, but this is it is not that I wrote the code or anything, but it's the very best that we have right now. And people have been developing this for decades, so it's a gigantic effort. Something about this simulation that I want to say is that you should not believe any of them. And I want to illustrate this with this movie. So what you can see here are 6 different simulations. Same cosmology, same initial conditions. The only difference is that this simulation has been run with different codes. There are different ways to solve the hydrodynamical equations, SPH, moving mass, AMR. And also because we don't know the physics of supermassive black hole, this thing that I was telling you before. Different groups are basically writing equations in different ways. But we still don't know which one is the group. What I can tell you is that all the simulations are able to reproduce basically the things that people get, things like the abundance of galaxies with different stellar masses or other properties. So all these simulations really reproduce all these things. But when you look at them and you compare them, you can see that they are like very, very big, right? So which one should you trust? I think you should not trust any of them. And that's the very important thing, right? Right now, we don't have a single simulation that is able to reproduce the real loop. This is the very best that we have, but there are different flavors. And what you want to do is to develop models that, at the very least, work in all these ways. This is the only hope that you will have. You have a model that works on all of this. This is not still enough to make sure that it's going to work with real data, but it's, I think, necessary.
Is this called comparison?
What do you mean? Yes, of course, I can give you.
No. I mean, one where systematic code comparison is done. I mean, I remember the previous early 2010s, like for hydrogen.
I see.
But I have never seen such a systematic study with cosmological.
Yeah, probably not. Probably not. Are you aware of the Agora problem?
Yes.
They compare this for individual galaxies. At the level of cosmological simulation, I don't think so. We have in our case, but in our case, let me show you the next movie. What we do is that all the simulation has like different, let's say, initial conditions, different cosmology, and different astrophysics. So we don't really want to do a code comparison because our way to think about this is that all these things are pretty much wrong. So you can see different simulations, and they were designed to do machine learning, so different initial conditions, different cosmologies, and also different astrophysics. So all this astrophysical model has some free parameters, how much energy you release with the supermassive black hole, a free parameter. So we vary these parameters, and that's why you can see that here there is much more red than in other one. So what you want to do is like, you want to vary cosmology, but then you also want to vary astrophysics. Because ideally you would like to marginalize over the astrophysics part that you don't trust.
But to do that, you need to sample the parameter space well enough, right?
Yep.
And right now there are biases in the community especially is, I mean, my expertise is in star formation, and I can tell you that everybody pretty much has the same thing, and it knows magnetic field.
Oh, yeah.
Okay,
Yeah.
so the parameter space is not uniform with calculus. Just
Exactly. That's also a little bit our idea with all these codes, because they all do different assumptions. And I'm not an expert on all these things. In Lustig TNG, we have magnetic fields. In Ramsey, we have magnetic fields. I don't know if this is at the level of formation of stars.
no,
That I don't know.
yeah. But the star formation there is a field.
Yeah.
Things are not really done properly.
Yeah.
They are biased in one way. And the difference between Ramses and the Lustig TNG is even worse, because one constraint uses constraint downstream, right? So B is 0. The other is not. And if you see B not, right? So
Exactly. Yeah. But yeah. So if you have also other simulation, please, let's talk later. So this is basically the last thing that I want to say. You know, if you run one simulation and you select all the galaxies and you construct the graph, this is what we do. You know, it's kind of a weird graph. It's not a connected graph. It's you know, it's just multiple how to say connected components. And I can tell you later why. So what we do is like we run 1,000 simulations with a single code. In our case, it's Astro, one of these simulations that I show you. In this 1,000 simulation, we vary mode and we vary astrophysics. For every simulation, we have a graph like this. And now what we do is taking all these simulations, we train a GNN to go from a galaxy catalog directly to the value of the cosmological path, marginalizing over astrophysics, field level.
May I ask something?
Please.
So what did you pick the galaxies here? This is hydro,
Yes.
from hydro simulation. So how did you pick the galaxy?
What do you mean? How do you
How did you define one?
Oh, yeah. I mean, the galaxies are identified by an algorithm. It's called affine, but you can use Rockstar. So basically, my understanding of this is that once you have like density large enough and particles are really visualized, then basically you define this as I.
Yeah, my question is, do you define the galaxy with just find the overdensity of dark matter of the subhalos and then you say this is a galaxy, or did you use the luminosity of the?
No. So my understanding of this is that you start first with the Friends of Friends. Are you familiar with this? So you connect particles that are within a given distance. Then you have already some kind of halo, defined like that. Then the next thing that you do is to find the center of the halo, and then you draw spheres until.
So this is dark matter galaxies.
No. This is like full hydrogen. So you do this with dark matter, gas, stars, black holes, everything.
Yeah.
And what else? And then you also remove particles that are not visualized. So, yes. In our case, I think we select galaxies above a certain stellar mass, then to the night.
you remove subtract.
What do you mean by subtraction? These are galaxies.
No, these are
includes
Exactly. This includes central satellites, everything. Okay. Exactly. So, what happens? You train your model on simulation, run with the same. Now you test your model on simulation, run with the same code, but with new parameters. You know that the network has never seen. So this is for the case of omega matter. So this is like the true value, the predicted value. And for instance, imagine this point here. This point here is a simulation. In simulation, you have a galaxy catalog. You construct the graph. You pass into a neural network, and the neural network gives you the mean of the posterior and the standard deviation. So you can see that the closer that you are to this line, is like you are able to recover, to define the true value. So this works very well. In this case, it's simulations, tested, run with the same code that I use to train the simulation. This always works, I can tell you. When you train on one code, you test on that code, that's what I want. That's always. What usually doesn't work is like when you now change the code. because you have seen before how different all these things are. So, you know, so exactly. So you have like that simulation, a galaxy catalog, and then you have a method. So what happened when you test this on simulations run with other people? So this is for simulation run with Villaescusa-Navarro. The network was trained with Astro. It works. Simba, it works. Magneticum, it works. This is Villaescusa-Navarro, but the parameter space is much larger. It works. Eagle, it works. Francis, it works. Some people ask me, this doesn't work, and that's true. So the thing here is that supernova feedback was so efficient that there is only one galaxy in this universe. So then, yeah, maybe you expect that it will not work. And then, you know, it really works. So
all these are for Omega Matter specifically?
This is all for Omega Matter. For SID9, the constraints are not very good. That's why we didn't show them.
Yeah, but Omega Matter one could argue that regardless of the simulation that we use or the code, it's basically gravity, right? So gravity will form the halos or the sub-halos, which dominate the dynamics, and then you will have your very recipe that they will populate this with the gravity. So that makes sense. No, but the gravity used to create the graph. I found like yeah.
Yes.
Yeah,
So what I can tell you is that the only way that this works is because we're using position and velocities. If you only use position, it doesn't work. You train on Astrid, it doesn't work at all. So our galaxy catalog has positions, velocities.
no, without
If you only use position, it doesn't work.
you cannot retrieve
It doesn't work. So that's still an open problem. And you know, so I have this, you know, I mean, and that's the last. So Helen is an undergraduate student at Princeton, and she was able to basically, you know, combine symbolic regression, which is, you know, a way to get analytic equations, because, you know, the GNN is a really black box, right? You don't really understand it. But she was able to derive this formula. This is a horrible formula that I don't really understand. But believe me that you can use this formula with galaxy catalog and all the thousands of relations that I showed you before, and you're going to get Omega Matter. So what I believe, what is happening is that, you know, when you have position and velocities, there are some laws that you need to respect, you know, like the continuity equation. Galaxy. Yes, I think something like that. Exactly. With position, you can really put galaxies in any way that you want. Yeah. But in phase space, I don't think you have that freedom. Yeah. So I think this is why it works.
May I ask one more thing? So those networks that you train, the data that you feed the network is 3 dimensions or 6 dimensions?
No.
Does it work in projection?
Very good. So we use 3 spatial positions, X, Y, Z, and only the radial velocity. Only the radial velocity.
Yeah, but in reality, you have one less degree of freedom, no? Because you have the position in the plane of the sky, and then you have the radial, the line of sight velocity,
sure,
which is coupled with the distance.
Sure. I mean, you observe galaxies in redshift space. So, I mean, this can be used if you have peculiar velocity sounds.
Right, right.
In that case, you have position and velocity.
Yeah.
But you also have errors in the velocity.
So the velocity you feed is a peculiar velocity, right?
It's a peculiar velocity. Exactly.
You need spectroscopic errors. No.
Velocities or observed velocity?
Very good question. So here we assume that the velocity is non-perfect, right? That's what will work very well. We have a follow-up paper where we assume that if you have a 10% error in the velocity and it still works, we were told that 10 to 15%, that's kind of the error that you expect for peculiar velocity surveys. Yeah, so that's more or less what you expect, 10-15%. But this is also like very local volume, right? You cannot measure peculiar velocities at very high density. So, you know, not that we're solving the field, right? But it's I think, very cool.
Yeah,
That you can go to, we are going to distance of 2 kiloparsec. 2 kiloparsec, right? This is incredibly small. I think no one has ever done this. And this is like field level, marginalizing over baryonic effects. And you show that, it's robust to basically the code.
Omega lambda?
Well, I mean, here we're assuming that omega k is 0. So if you know omega matter, you know omega lambda. So I'm going to stop here. Let me show you this movie. This has nothing to do, and probably, but I think it's cool. I spent way too much time. So these are now, other simulations that we're running now. This is much higher resolution. Maybe some of you might be interested on this. The idea here is, to run these kind of zooming simulations at much higher resolution. You will see we have like beautiful galaxies with all the spiral arms and all these things. And what we're doing is creating a lot of these galaxies, varying now dark matter. We assume that you have more dark matter or atomic dark matter or all these kind of things. And the idea is that if someone gives you galaxies, run with different dark matter models, maybe you can train a model, and the model will be able to identify some features there that might tell you something about that. So I'm going to stop here, and thank you very much.
Any question?
Yes,
Idiot? Yeah.
No.
Have you tried your method with in real data?
Very good question. Very good question. So, please.
One more question. In general, in that kind of training, do you start somehow for the uncertainties, the features that you said, for example, in each slope of the graph, you said that you have a number of features, like the velocities, like distance here. But okay, in simulations, maybe you don't have that, but in real data, you have that. And I was wondering how you can include this information in your training.
So for the first question, have we applied this to real data? Yes, we are waiting for the Nobel Prize. So no. So the problem about this is that these simulations are very small, 25 megabytes, right? So we are also missing all these large scale units, right? So I don't even think that this is, I don't think you can even train on this simulation and apply to real data. So something that we're working now is like, these kind of ideas also work if you use semi-analytic models. And semi-analytic models are not full hydro, are much faster, so you can now go much larger volumes. So probably maybe in a few years, maybe we can try to do this. The second thing is what she was asking. In principle, we have a second paper where we put error bars for the position of the galaxies. Spectroscopy, as far as I know, is still very precise, right? So the error bars are not super large, but velocity is there. And, we put errors for the position and for the velocities like 10 or 15%, and we show that still this thing works. It's still robust. Your error bars increase, of course, but still things are robust, which is the most important. Please.
Okay, so my understanding is that the features that we use in the training is going to allow numbers like the distance, the velocities of the galaxy. It would be useful if you start adding other information of the galaxies, like information rate, stellar masses, metallicity, whatever value added information that we have in the galaxy.
Very good question. We did this. So the problem about this is that this is not robust to astrophysics. You can use position velocities and all these things. You train on this, it doesn't work on the other thing. The galaxies are too different. So that is make things even worse. Your error bars gets much tighter. You get super tiny error bars, but it's not robust. So then,
I think the
edge features are taking only the distance of the relative velocities between the lights.
So what we do is, so in this case, for the node features, so the node features are only the radial velocity.
Yeah, and then the edges.
And then the edges, we have like distances and angles.
Oh.
And that's
And on the, would it be, but it would improve relative velocity between the lights.
relative velocities.
Not included in the technology.
Yeah, I mean, in principle, the network should be able to compute relative velocities. So maybe if you put it more explicitly, it will work better, but not sure.
Can you imagine the interpretability slide? Yes, that's cool. So you get the number out of your map or the model. Can do something with it. Connect it to some physics or anything, or just get numbers. That's nice.
We try very hard. I mean, if this means something to you, we talk with a lot of people that are more, like Ravi Shed and Martin White, all these people that are maybe a little bit more analytical. None of them were able to say anything. So I believe it's related to the Liouville equation, continuity equation. But yeah.
So can you still keep the name interpretability if you don't understand anything about the method?
That's a very good question. Some people, I mean, as you know, some people talking in this symbolic regression is that if you get an equation, it's going to be more interpretable. I'm not sure if this is more interpretable. So
put the word in quotation marks. You're fine.
yeah. I know. But some people like formula. I mean, yeah.
Okay. One last question.
So, fantastic stuff. So, in your model, you take the simulation, you generate the graph, and then you do the embedding, which is estimating the cosmological parameters. You would be interested, I guess, in taking, the vice versa, taking the cosmological parameters and simulating something. So, have you thought about using this, self-supervised, this machine learning framework where you do both at once? So, you start from a model, you get parameters, and then you end up with a graph.
Exactly. People have done this, and these are the generative models, right? Where you basically generate the data, and by generating the data, you can also compute all the posteriors and all these things. So yeah, people have done this, and you can use either graph neural networks or transformers. And I didn't have time to talk about this, but this is precisely what I wanna talk up with these things. It's one of these generative models where you generate the data given the parameters, and then you can estimate the posterior. So yeah, you are.
Okay.
Thank you.